might take a bit of extra time so that I can finish the solution and the corresponding parameters. Fine. So let's start with the point form or phasor form of our wave equation which we derived. This is del square Es minus is equal to j omega mu into sigma plus j omega epsilon Es. So this is the wave equation that we derived in the phasor or the point form in two classes before. So I can write this as del square Es minus gamma square Es is equal to 0, where gamma square is equal to j omega mu into sigma plus j omega epsilon, and this is called as propagation constant. We have seen a similar gamma in transmission line also, same with the same name, which is propagation constant. Okay. Now this is regarding electric field. With respect to magnetic fields also, it is exactly same, except that the electric field will be replaced with magnetic field. Okay. And these equations are actually called as homogeneous vector Helmholtz equation. Okay. Fine. Now we are going to make some assumptions which we will generalize it later. These assumptions are made so that the derivation will become easier. But these assumptions are valid assumptions and we can generalize those assumptions later. And in the last class, we have seen a problem that electric field has orientation in one particular direction and has variation, or the propagation is a different direction. We are assuming that all these directions. So what we are assuming is like this. Electric field is oriented in x direction okay, that means it is ax cap, and magnetic field is oriented in y direction, because always magnetic field and electric field will be perpendicular to each other. The wave is propagating, so I write electromagnetic wave as EM wave propagates in z direction. So all these are positive. All these are like positive directions. Okay. The next assumption that we are going to make is electric field variation is only along z. That is, electric field is a function of z. So it doesn't depend on x or y. Okay. So these are the main assumptions that we are making. If any further assumptions are there, we will do that on the go. Right? Okay. Now let's look at this equation, del square Es. Now Es is a vector, it's a phasor which has a vector, and it can be written as some Exs ax cap plus Exy ay cap plus Exz az cap, where xs, xy, xz are, sorry, I think this should be ys and zs. So XS, YS, ZS are the components of the phasor notation of electric field along X, Y, and Z directions respectively. Okay. Now we say that E is oriented in X direction, which means all these terms will be zero because it is oriented only in X direction. And E is varying in Z, means EXS will be a function of Z. So in the last class, we have seen that electric field equation, omega t sum 20 sine of omega t minus beta z, a y cap. So that x omega t minus beta z, the variation is only along z. So something like that. Okay, fine. So when I do del square ES, this is basically dou square by dou x square EX plus dou square by dou y square ES plus dou square by dou z square ES. Okay, and ES has only EXS of Z. So I write Z in both the form this or this. Actually, both are okay, both are same. Okay, and so all these ES are of is a function of Z. Okay, means when you differentiate with respect to X or Y, the value will be zero because EXS is only a function of Z. Something like omega t minus beta z, where it is only a function of Z. It doesn't depend on X and Y. So del square ES is equal to dou square by dou Z square ES. That is equal to dou square by dou Z square EXS of Z. Okay. Similarly, we have the next term, which is gamma square ES. So gamma square ES is equal to, now ES has only one term, which is this one. So I can write gamma square ES is equal to EXS of Z AX cap into gamma square. Okay, and remember EXS is magnitude, it is not a vector. Okay, so this is magnitude because it's a component along X and it is not a vector. Fine. So our equation now becomes dou square by dou Z square EX of Z is equal to gamma square EXS of Z. Okay. Now the direction is along AX cap. Fine. So we want to solve this equation. And you can see that this solution of this equation is similar to that we have derived in transmission lines. And the solution is actually given as EXS of Z is equal to E0 e raised to minus gamma Z plus E0 dash e raised to plus gamma Z. Okay, so this is the solution of the wave equation in terms of electric field. So in terms of magnetic field, this equation will be like dou square by dou Z square EX or it should be H. Now we say that H is oriented in Y direction and has a component AY cap, and H also varies only along Z. Okay, let me write that also. So H and E varies only along Z. So I can write this as H y s of Z is equal to gamma square H y s of Z. So whatever we are deriving for electric field is valid for the magnetic field also. Okay. So my solution to magnetic field is Hys of Z is equal to H0 e raised to minus gamma Z plus H0 dash e raised to plus gamma Z. Okay. Now there is one assumption that we made, that the wave is propagating in positive Z direction. Okay. If you look at these two equations, you see that there are two components, and we know that the first component is the wave propagating in, this is wave propagating in plus Z direction, and this is the wave propagating in minus Z direction. But we already made the assumption that the wave is only propagating in plus Z direction. Okay. And also, since this is an unbounded medium, so basically whatever wave is propagating in minus Z direction, it is assumed to be a reflected wave. So if the wave, transmission lines are bounded mediums, but we are considering here an unbounded medium where there are no structures to block the wave. So there is no chance of reflection. And we already assume that the wave is propagating in Z direction. So by assumption, wave is in plus Z direction. Implies my solution to the wave equation is Ex of Z is equal to, let me write this as Exs of Z is equal to E0 e raised to minus gamma Z. We neglect or we remove the term of the wave propagating in minus Z direction. Similarly, I can write Hys of Z is equal to H0 e raised to minus gamma Z. So this is the solution to our wave equation. Okay. So we did, what we did was we removed the wave propagating in minus Z direction because of two reasons. One, we initially assumed that wave is only propagating in plus Z direction. Two, since it is an unbound medium, there will not be any reflection that is along minus Z direction. So we remove that term. So this is your final solution. Okay. Now let's analyze this solution. Okay. So the solution is in phasor form. So if you write this in the actual E, so this is equal to the real part of Es e raised to j omega t x cap. Okay, so this is actually equal to the real part of, we know that Es has only one component, which is Exs of Z e raised to j omega t. It is propagating along the x direction. Let's substitute the values. So this is real part of E0 e raised to minus gamma Z e raised to j omega t x cap. Okay, here the value E0 and H0 are constants. This is actually a magnitude and they are constants. Okay. Fine. Now let's expand this. Gamma is j omega mu into sigma plus j omega epsilon. Make sure you understand or you know this equation. It will be asked everywhere. We will be deriving a lot of equations in this class and next. Make sure you note down all this equation, write it down in a piece of paper so that you can always refer them. Okay. Now this is actually a complex quantity because you have a term of j. Implies I can write gamma is equal to alpha plus j beta. Okay. So I can substitute E is equal to the real part of E0 e raised to minus of alpha plus j beta into z e raised to j omega t, and I'm taking the x cap out. Okay, that's a unit vector. You can take it out of the real. So this is equal to real part of E0 e raised to minus alpha z e raised to minus j beta z e raised to j omega t x cap, and this can write by combining the j terms e raised to minus alpha z into e raised to j into omega t minus beta c into x cap. So this quantity here is always real. This is always real. So you can always take it out. And this quantity is actually our cos theta plus j sin theta. So this output will be multiplication of the cosine of the omega t minus beta z angle and E0 e raised to minus alpha z. So I can write finally E as E0 e raised to minus alpha z cos of omega t minus beta z x cap. And this is the expression of the electric field component of the electromagnetic wave. This is your expression. And you see that the variation of electric field is sinusoidal, means it is some kind of a cosine wave. So this is a cosine wave. Okay. And this is the frequency, which is omega. And Z is the direction of propagation. And the wave varies both in time and frequency. So this variation in time and space, it is Z. Okay. Now, when you have positive Z direction, so the direction of propagation is positive Z. Okay. If we had negative Z direction of propagation, then this minus would have been plus. Okay. That we will see in a problem. Okay. And this is actually an attenuation. Okay. And AX cap is the direction or orientation of electric field. Okay. And E0 is basically the, you can say, the amplitude. Maximum amplitude, something like that. Okay. So since e raised to minus alpha z actually attenuates the wave, alpha is called as attenuation constant. And beta is in the phase of the wave, which is omega t minus beta z, is actually the phase of cosine wave. This is called as phase constant. Okay. Now this we have derived for E. Similarly for H, we can write as H0 e raised to minus alpha z cos of omega t minus beta z, but the direction is a by cap. We'll see why this is a by. We have actually seen in the last class when we did that problem. When you do del cross E, which is actually a version of H, del cross E, make sure that whatever H is coming will be in the perpendicular direction of E. Okay. So this is the expression for H. So whatever derivation we have followed for electric field, you can follow the same derivation for H. So I am not again deriving for H. Okay, fine. Now, we have derived the wave equation, etc., etc. We now want to know what is the expression for alpha and beta, because we have the gamma expression as like a mixed terms of real and imaginary parts. So we want to derive a general expression for alpha and beta. So that is bit of a derivation which, let me be careful in understanding that. So derivation for alpha and beta. Okay. So gamma is equal to alpha plus j beta, which we have already seen. Let's take the square. Gamma square is equal to alpha plus j beta into alpha plus j beta. So this is equal to alpha square minus beta square plus 2j alpha beta. So this is your normal complex multiplication. Now what is the real part of gamma square? This is equal to alpha square minus beta square, because this is the real part and this is the imaginary part. Right? Okay. Now let's do the magnitude of alpha square, sorry, gamma square, which is basically the square root of sum of squares of real and imaginary part. So I can write this as root over alpha square minus beta square the whole square, which is the square of the real part, plus 2 alpha beta the whole square, which is the square of the imaginary part. Okay, fine. Let's expand this. So this is equal to square root of alpha raised to 4 plus beta raised to 4 minus 2 alpha square beta square, that is the first term expansion, plus 4 alpha square beta square, the second term expansion. Now let's combine these two. So just a simple addition. Okay, and both are of alpha square beta square, so I can just combine these two and I can write this as square root of alpha raised to 4 plus beta raised to 4 minus, sorry, plus 2 alpha square beta square. Okay, this expression is actually alpha square plus beta square the whole square, right? So if you expand alpha square plus beta square the whole square, you will get alpha raised to 4 plus beta raised to 4 plus 2 alpha square beta square. So when you take the square root of this, you will get alpha square plus beta square. Fine. Okay. So let's say this is equation number 1 and let's say this is equation number 2. So equation number 1 says real part of gamma square is alpha square minus beta square. Equation number 2 says the magnitude of gamma square is alpha square plus 2 beta square. Now let's simply add 1 plus 2, that is 2 alpha square. Okay, So I can write the real part of gamma square plus magnitude of gamma square is equal to 2 alpha square. Now you see that now we have reduced the equation as an equation of only alpha. Fine. Now we know the values of gamma. We know that gamma is equal to j omega mu into sigma plus j omega epsilon. Okay. Let's expand this again. This is j omega mu sigma minus omega square mu epsilon. The real part of gamma is equal to minus omega square mu epsilon. Or sorry, this is actually gamma square. I'm sorry. So I think I have written it somewhere again as, so this is actually gamma square. Okay. And let me see if I have made the same mistake somewhere else. Okay, this is correct. Okay. So gamma square is j omega mu into sigma plus j omega epsilon. Fine. Okay. Now let's do the magnitude of gamma square. The magnitude of gamma square is square of the real term, which is minus omega square mu epsilon the whole square plus the square of the imaginary term, which is omega mu sigma the whole square. Okay. So let's say this is equation number 3 and this is equation number 4. So basically I want to have 3 added with 4 to get this equation, which is real part of gamma square plus magnitude of gamma square. So when you add 3 plus 4, you will have the real part of gamma square plus magnitude of gamma square is equal to square root of minus omega square mu epsilon whole square. The minus will get positive, so you can write this as omega raised to 4 mu square epsilon square plus omega square mu square sigma square minus the third one, which is omega square mu epsilon. Okay, fine. Now I am going to do a little bit of approximations and manipulations. Okay, let's do this is equation number 5. So in 5, from the term inside square root, take omega epsilon, sorry, omega mu epsilon, omega square mu epsilon out. Okay, so I can write equation number 5 as square root of omega square, sorry, omega raised to 4 mu epsilon, this whole square out, multiplied by 1, which is this. Okay, now when you take omega raised to 4 mu square epsilon square out from here, okay, you will have 1 plus sigma square by omega square epsilon square. Just want to verify, you just take this inside, you will see that you will get this expression. Okay, minus omega square mu epsilon. Fine. Okay, so if you look at this, this is all in terms of even powers, right? So I can take this out of the square root. So this I can write as omega square mu epsilon square root of 1 plus sigma by omega epsilon the whole square minus omega square mu epsilon. Right? Now you see that omega square mu epsilon is common in both the terms. So again, I take out from the complete term. So I can write this as omega square mu epsilon multiplied by square root of 1 plus sigma by omega epsilon the whole square minus 1. Okay. Now, equation number 5 is, this is actually 2 alpha square. So I can write 2 alpha square is equal to omega square mu epsilon into square root of 1 plus sigma by omega epsilon the whole square minus 1. Let's bring 2 to the other side. So alpha square is equal to omega square mu epsilon by 2 multiplied by square root of 1 plus sigma by omega epsilon the whole square minus 1. So alpha is equal to, you take the complete square root of omega square is omega, so that will come out. So this is omega, the rest will come inside the square root. Mu epsilon by 2 multiplied by square root of 1 plus sigma by omega epsilon the whole square minus 1. So this minus 1 is actually outside the square root. Okay, let's put a bracket here. So the value of the attenuation constant in general is omega square root of mu epsilon by 2 square root of 1 plus sigma by omega epsilon the whole square minus 1 minus 1. Yeah. And this is the general form of the attenuation constant. Okay. I hope you have understood this. Okay, this is bit of a derivation. Only thing that you might get confused is in this part, when you take omega raised to 4 omega square epsilon square out, how is the expression coming? But I think if you just write it down, you will understand this. Okay, you can just take it inside and verify. Fine. Now, in a similar way, you can do derivation for beta. So instead of taking the real part, you take imaginary part, and you can square it up, and you can see, or you can subtract real part of omega square minus magnitude of omega square to get to beta square. Okay, so you get beta as omega square root of mu epsilon by 2 into square root of one plus sigma by omega epsilon the whole square plus 1. That's only difference. So in alpha you have minus 1, in beta you have plus 1. Okay, and that is your beta. We will reuse these equations when we look at different kinds of medium, lossless, low loss, etc. So when you have all these kinds of medium, you will see that the equation will be very simple. So alpha will be like omega in the root over mu epsilon. That's all. Okay. So this is a general derivation. You can be used in any kind of medium if the medium is not specified. But if the medium is specified, it has lossless or lossy or something like that, then you can substitute those values and you will see that the value of alpha and beta are like very simple expressions, omega, mu, epsilon, or something like that. Okay. So this is the propagation constant. Okay, fine. Now, apart from this parameter, there is a parameter which is called as intrinsic impedance. And it is denoted by eta. Why it is there is because you see in your expression for E and H. Okay, so you see that in the expression for E and H, you have a term E0 here for E and H0 here for H, right? Now, what is the relation between E0 and H0? Is there a relation? And actually, there's a relation. The ratio of E0 to that of H0 is the intrinsic impedance. Okay, so your intrinsic impedance eta is equal to E0 by H0. And this is actually the impedance observed by the EM wave as it propagates through the medium. Okay, we are going to derive an expression for eta. Now that derivation is very easy. Okay, let's do that. Now we know that EXS of Z is equal to E0 e raised to minus gamma Z. And this is along the direction of AX cap. And EYS of Z, sorry, HYS of Z is H0 e raised to minus gamma Z, which is along Y direction. Okay, so I'm just mentioning the direction. EXS of Z will not have the direction along with it. I'm just mentioning it here, that's all. Okay, fine. Now, according to the Maxwell's equation, del cross ES is equal to minus j omega mu HS. This we have already seen. So del cross ES is equal to AX cap, AY cap, AZ cap, dou by dou X, dou by dou Y, dou by dou Z. Now you have EXS. It doesn't have components along Y and Z. So it is like this. So the determinant of this. So this is equal to dou EXS by dou Z AY cap minus dou EXS by dou Y AZ cap. Okay. Now we know that ESX varies or varies only in Z, implies the value of this term is equal to 0. Because when you differentiate Exs of Z S by with respect to Y, the electric field doesn't have any variation along Y, because of which when you differentiate with respect to Y, it becomes 0. Okay. So your final expression of del cross Es is equal to dou by dou Z Exs Ay cap. So this is equal to dou Exs by dou Z Ay cap is equal to minus j omega mu Hs bar. Now Hs we already know the equation. Minus j omega mu Hs is Hys offset Ay cap. Where Hys also we know, which is j omega mu. Hys is H0 e raised to minus gamma Z Ay cap. Okay. So again, I can write this complete equation as dou by dou Z Exs is E0 e raised to minus gamma Z, which we have derived. Ay cap is equal to minus j omega mu H0 e raised to minus gamma Z Ay cap. Okay. And Ay cap is there in both sides, which means both are in same direction. So I don't want to consider direction. I can just differentiate this with respect to Z. So when you differentiate with respect to Z, it is E0 minus gamma e raised to minus gamma Z is equal to minus j omega mu H0 e raised to minus gamma Z. Now e raised to minus gamma Z is there in both left hand side and right hand side. It will get cancelled out. Let's take the value of E0 by H0. This is equal to j omega mu by gamma. And you substitute the value of gamma. This is j omega mu by gamma is square root of j omega mu into sigma plus j omega epsilon. From where did we get this? We know the expression of gamma square here. So this is gamma square. So gamma is square root of this term, which we have written here. Okay. So I can write this as E0 by H0 is equal to j omega mu. I can write as square root of j omega mu whole square by square root of j omega mu multiplied by square root of sigma plus j omega epsilon. Because square root of product of two numbers is the square root of first number multiplied by the square root of second number. So the squares will cancel, this will get cancelled. Your final expression will come as E0 by H0, which is the intrinsic impedance, is equal to square root of j omega mu by sigma plus j omega epsilon. And this is the intrinsic impedance of the medium, expression of intrinsic impedance. And you see that the intrinsic impedance is a complex quantity. Okay, and this is complex. So it will be both resistive and reactive impedance, the wave will observe as it travels through the medium. Okay. Fine. So I think this is a good time to stop. We have a small portion left in this module, which is basically using this intrinsic impedance we'll go and find out something called as loss tangent, and we will analyze these equations in lossless, perfect conductor, and free space mediums. So that is a very simple analysis. It might take only 10 minutes. So by the next class, we'll finish module 2 and start module number 3. Okay. So I hope you have understood this. And just I am uploading all these lectures. Make sure you go through these notes so that you'll get, if you have any doubts, you can always ask me.